I have turned on. So the theme of my talk is a classical long-range system and kinetic theory. And I have 2 lectures today. So, yeah? Sorry? It's okay? It's okay for you? Okay. And I have 2 lectures today and tomorrow morning. And my plan, my current plan is like this. So today is day 1. I present a basic analysis of dynamics. I introduced the Brasov equation. So it is very used in the long-range interacting system. And then I introduced what is the stationary state of the Brasov equation and how to analyze the stability of the stationary state. And tomorrow, day 2, so I go to the presentation and present anomalies in long-range system. So Brasov equation have some the interesting feature comparing with a short-range interacting system. So I introduced some anomalies which appear in long-range system. So day 1 is rather the mathematical part, and day 2 is the physical part. Okay, let us start. I start from the very simple example of the analysis of dynamics. So simple example. So let us consider x. Derivative by t is fx. So now x is in Rn. This is a very generic system, so there's no distinguish between the short range or long range. So anyway, how to analyze this system? So first thing is stationarity. Where is the stationary point? So I say it's the stationary point xr. And then so it is very easy. We have to solve this equation. That's all. And then stability of x star, we have to analyze. Oh, sorry. Eigenvalue of so this one is a Jacobi matrix. So basically that's all. So we start from the searching the stationary point, and then we investigate the stability of the stationary point. That's all. Example of example is like this. So if we say something like this, so this, and x is now just in R. In this case, where is the stationary point? Very easy. So we have to solve, stationary point. Minus kx star cube equals 0. So it means x star is 0 or plus minus square root k. But this solution exists only for k plus. So now I can write down some phase diagram. So k in the horizontal axis and x star in the vertical axis. And we have the x star 0 as the stationary point and other branches of square root of k. And stability, to investigate stability, we consider the Jacobian matrix. Now, Jacobian matrix is just a derivative of f. So it means that k minus 3 x squared, and okay, that's all. So for k x star equals 0, so this one is k for x star equals 0, and minus 2k for x star equal plus minus square root k. So now we can understand the stability of these branches. Where is it stable? So x star equals 0 has a derivative k, and k negative part is stable. So this one is stable. And k positive, it has a positive derivative, so it is a negative and unstable. And for this branch, so this and this branch, so we have negative, because this one is a k, this exists for k positive, so minus 2k is negative, so this branch and this branch, this branch and this branch are stable. So this is the very basic analysis of dynamical system, and we will go to we will do more or less the same thing in long-range system in the Brasov equation. And so before going to the Brasov equation, I fix the system which we consider in my lecture. So model. So now I concentrate, so as simple as possible, I use the more or less very similar, very simple model. So I write down the Hamiltonian, n-body Hamiltonian. So it is j equals 1 of n and pj squared. Now I assume mass, all mass is unity. And then I have a double sum of j and k and the interaction function phi and q, qj minus qk. So this is my target system. So this one is to avoid the double count of this interaction term. So we have interaction between j and k. So once we get count j and k interaction, we don't need to count k and j. So I divide by 2. And this factor is the famous Kurt's prescription. And thanks to the nice introduction of the Mikhail, I skipped to discuss on this Kurt's prescription. So
you did phi 0 to be 0.
Phi 0, sorry?
Phi 0, there is no self-interaction.
Phi 0? Okay, so if we consider j equal k, it is phi 0. So it is not necessary that phi 0 is 0, because this is just constant. So, and for dynamics, the basic energy, the constant energy is not important. So it's not so important.
So if you take it to be a power law interaction, so when J is equal to K, it will diverge. So 1 by J minus K mod to the power of 5 you take, or you are going to take a mean field model.
Okay. So in general, maybe in this school in general, we need to consider something like this. So J minus K. And then I take alpha equal 0. Okay? So in my terminology, it is a mean field system, or otherwise all-to-all interaction system with equal weight of interaction. So the HMA, which has also been introduced by Mikhail, is reproduced by taking phi q equal minus something this. So this is very simplest case. Okay. I forgot to say the condition of phi. The phi should be even and periodic. So this assumption of periodic is periodic simplified problem. So phi q is a periodic variable. And evenness comes from the Hamiltonian nature, because potential energy between J and K does not change if we exchange the J and K. So it should be even and then periodic. Okay? And another point is I introduced the order parameter, which is sometimes said magnetization, because in this system, so we can imagine the XY model. So this part is a strange part for the XY model, but anyway, I introduced the kinetic energy term for XY model. And then the magnetization, order parameter of magnet is some vector. And I say mx and my. It is defined by so what is this? So now the n particles is confined on the unit circle like this. And then this m vector is the average vector. So this m vector is more or less something like this. So if we introduce the absolute value of this vector, then m with the uniform distribution is 0, and m, so n particles get at the same point is 1. So it indicates how large cluster we get. So this one is 0, no cluster, and this one is the strongest cluster.
I mean, in the thermodynamic chemistry, otherwise n going to infinity. If n is finite, you won't get exactly 0, I guess.
Okay. So if we consider uniform distribution in finite system, then we get something like this one by central limit theorem. And if we take n to infinite limit, then it goes to 0. And now I introduce the equation, the dynamical equation of motion. We have Hamiltonian, so we have the canonical equation of motion. So it is Qj prime is dH dP, and Pj dot is minus dhn dqj. So for HM model case, we get, so this one is just a Pj, so very simple. So we get the Newton equation like this, minus the Hamiltonian. Okay. And the HMX case is very simple. Minus 1 over n and sum and sine. So this is the HM. So dynamical equation of HM model. So I give two remarks. First, so maybe it's better to write down like this. If we move this n factor to the time factor, then we get t over square root n equal non-scaled system. So Katz prescription introduced the time scaling of square root n. So in the example of Mikhail, it was time scaling was n, but in this case, the time scaling is square root n. So it depends on the system. And second remark is, so this one, we can expand something like this. Yeah.
Yeah. So what do you mean by time scaling is square root of n? And do you say that is the time it takes to reach the steady state will increase as square root of n?
No. So I just comparing the. So if we omit the Katz prescription, then we get this kind. So without 1 over n prefactor. So in that case, this one is the time scale of non-scaled system. So I say just that's right.
Shouldn't this,
yeah.
The difference that I got as n and you get square root of n, is that simply because it's a second order differential equation for the equation?
Exactly.
So should not depend on the specific model. Another classical model would give the square root as well?
Yeah, so if we consider, for instance, if we consider the, so where is my Hamiltonian? Okay, so the top Hamiltonian. So the kinetic term introduced the second derivative. So if we consider that kind of class of Hamiltonian, then we get the second order derivative with respect to t, and then time scale should be square root n. And second remark is we can expand the sine part this, and the sum part act on this and this, and then with the sums of this factor 1 over n, this part go to mx, and this part go to my. So we can write down the equation of motion as mx sine qj plus my cosine qj. So the message of this equation is the twofold. The one is j's particle interact with the other particles only through the mean field. So if I write down the figure, so we have mean field, I mean to say mx and my. And then we have n particles. So each particle interact like this. So we don't need to take care about the interaction between the I, j, and k or something like that. So that is the first. And the second part is this is a good expression for performing numerical computation. So okay, so this one. Don't use this expression for making a code, because this sum is a cost of order n, and we need to compute the n particles. So the cost of computation should be order n squared if we use this expression. But with this expression, so first we compute order parameter with the cost of order n. And then this order parameter can be used for n particles. So the cost is 2 by order 2 by n. So order n and order n squared is very different. So I strongly recommend to use this expression. Okay. And then for this model, I introduced the Brasov equation. So now we have this kind of ODE of n particles, and it seems very difficult to analyze by this n-body system. So how can we analyze this system? So strategy like this. So we write down the q-axis here and p-axis here. And q-axis is periodic, not pi and minus pi. And then I put the n particles on this plane. So Q1, P1 here, Q2, P2 here, and Q3, P3 here, and blah, 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 blah. So I put n particles on this plane. Okay. And if we continue for the infinite, so n, very large n, then it is similar with the concerning the distribution. So in this picture, around here, we have the high density. So we have a high density distribution. And here, the distribution is very small. So we change the picture from n-body to distribution. Now we write the distribution is big F. It depends on Q and P and T. and distribution, the meaning of distribution like this. So this is a fraction of particles in the region of Q plus dq times P plus dP at time t. So we sorry?
So this F is defined with the single particle phase space. So what is the second plot?
This one? This
Single particle phase space?
Yes, this one is a single particle distribution. So we say that this F is a one body distribution. Is it clear? We just put, so this one is just one-dimensional variable, and this one is one-dimensional variable, and we put the n particles on two-dimensional plane, and then we consider distribution of n particles. So now I have, we have f distribution function f. How about the evolution? How to get the evolution of f? So we start from n-body Hamiltonian. So I change the manner of the description, so like this. So this is a Hamiltonian. And then now we concentrate on the jth particle because we are considering the one body distribution. So we consider F-dependent Hamiltonian depending on P, Q and P and T, unfortunately T. And this one is one dimension. So we concentrate on this part, and we eliminate the index, not important index j. So we put p squared over 2, and plus this one. So what is this? So now we have n particle average in this part. So I replace this n particle average with distribution average. Oh, sorry, maybe it's something like this. And maybe not good. Is it clear? So this one is a Hamiltonian which governs the temporal evolution of jth particle. As I said, the jth particle, the time evolution of jth particle is governed by mean field. So this one is the corresponding mean field potential.
So you are already taking the thermodynamic limit or no?
Yes, yes. So I took the infinite limit. Then we get this one body. So this one is a one body distribution, and similarly, this one is called one body Hamiltonian. And how about so Hamiltonian is okay, and then how about the distribution, temporal evolution of distribution F? So F is the fraction of particles, and the particle does not vanish, and particles are not created. So it means that the number of particles are conserved. So we introduce the equation of continuity. So it is this one, and then I start from q derivative with the velocity for the q axis and f plus p part. And what is this velocity? Of course, we consider the Hamiltonian system, so this velocity should be Hamiltonian vector field. Oh, I have no space. So BQ and BP should be Hamiltonian vector field, but with this one body Hamiltonian. So essentially, this is the so-called Prof equation. And now we have, so this one is a vector field. So Hamiltonian nature gives divergenceless of vector field. Oh, sorry, this is color. So divergenceless induce a little bit to simplify this equation, because derivative of this and derivative of this cancelled out. So remaining part is plus BQ outside of derivative. Sorry, I introduced a Hamiltonian vector field. P minus okay, so this is the Prof equation.
Why did you need to put divergence of V to 0?
Sorry?
Why did you need to put divergence of V to be 0?
B2 is B0. So
Divergence of V.
Divergence? Okay, so if we compute this part, for instance, we get, in general, this one f plus this one. Okay, and the another term is f plus dp and df dp. So the summation of these two terms have this part and this part. So this is divergence. So if divergence is 0, then we can eliminate this one, this one.
Yeah, if that is true, so I'm asking why do we need to put that to be 0?
So
No, it's a consequence of the Hamiltonian structure.
yeah, so do you mean that why the divergence is 0 is realizable? The reason of the divergence is 0? Okay, so it is very simple. So now you say that so divergence of B is divergence BQ dq and VP dp, and VQ is this one. And dp is this guy. So it's 0. So this is a Brasov equation, and we study this Brasov equation from now on. And I give remarks, maybe 2 remarks. Okay, 2 remarks. The first remark is this is the temporal. This is the equation for the temporal evolution of F. But if we use HF, Hamiltonian, and the Hamiltonian depend on F, so to determine the temporal evolution of F, we need Hamiltonian. But to compute Hamiltonian, so the top part, to compute Hamiltonian, we need F. So the Hamiltonian is necessary to F, and F needed to H. So we have to solve self-constantly. So this is the first remark. And second remark is the difference between the Brasov equation and the Liouville equation. Maybe many of you know the Liouville equation. And the Liouville equation looks like this kind of structure. So Liouville equation, what is Liouville equation? Liouville equation, we consider an n-body distribution function. And then time evolution of this n-body distribution function, we need sum here, and then k equal n, 1 to n, and n-body Hamiltonian come back here, and q k minus qk pk, okay, equals 0. So the structure is very similar between the Brasov equation and the Liouville equation, but the physical concept is completely different. So take care. Why? In Liouville equation, we have information of n particles. So this one, so okay, so Q1, blah, 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 and Pn, we consider this 2n dimensional phase space. Then so Fn is a function on this big phase space. And one point is, so this one point is one system. The distribution of Fn means now we are considering ensemble of systems, okay? But in Brasov equation, F is constructed by n particles of one system. So in Liouville equation, it is we consider ensemble of systems. But in Brasov, so F is a one system, temporal evolution one system. So it means if we prepare the initial distribution of n particles, and we want to know the temporal evolution of these n particles, then it is approximately considered by Brasov equation. We don't need to consider the ensemble of the system. So this is an important difference between Liouville and Brasov. And maybe you can ask me why this distribution, Brasov equation is okay for describing the long-range n-body system. Now we have mathematical justification of the Brasov description. So I introduced the mathematical justification. I have place? Okay.
Can you construct classification in the mean field?
Sorry?
You can construct classification in the mean field limit.
Sabiti?
Classification.
Brasov equation?
In the mean field limit.
Yes, yes. So at least mathematically, we need the mean field interaction. But probably it is possible. It may be possible to extend this kind of Brasov equation to the alpha Brasov equation. But I don't know. At least I don't know the mathematical justification for the alpha Brasov equation. So now I just restricted myself to in the alpha equals 0 case. So mathematical justification. Sorry. First, I considered so let Qj t and Pj t of the set of this one is the solution to canonical equation of motion. And then we consider the discrete distribution. So what is this? This is just maybe I have very long blackboard. Okay. The top part, the top left panel describes the n particles on two-dimensional plane. And if we construct forcefully construct a distribution function, so discrete distribution function, we get a delta function on each particle. So the previous my distribution described the n-body picture. Okay, so this is more or less the n-body picture. And the fact is, this is a solution to Brasov. So this is fact. So if we introduce, substitute this discrete distribution into the Brasov equation, it holds. And then the theorem say so let f t and f dt are solution to Brasov. And f0 and fd0 are corresponding initial state. And then we can say that if gradient of potential is bounded and Lipschitz continuous, then we get the estimation of the distance. So this one is some distance. So it is, sorry?
What are your subscripts? T what?
D, so I magnify my letter. So it is D, B, L. So because this one is a bounded
Okay.
lip sheet.
Okay, fine.
What is the word between before lip sheets? Is that
Bounded. Bound.
The word is bounded.
So the absolute value of gradient is that does not diverge. And C, this C is a depend on only phi. So I skip the detail of the bounded Lipschitz distance, but anyway, that is some kind of distance.
So solution to the Lassard equation is not unique. I mean, that's a good point.
Sorry?
So the solution of Lassard equation is not unique.
Not unique. So this theorem says just we consider two solutions, and so one solution this and another solution this, and we consider the distance between the two. And initially, we have so this is the initial distance between the two. So something like Lyapunov exponent or something, if we want. So we consider the initial distribution, initial distance, and finally, so at t, that distance becomes dt, all right? And we consider this kind of distance. And how this distance is bounded by the initial condition. So we can bound it by exponential function.
So C is positive.
C is positive. And negative is magnifique. If C is negative, it's okay. So this theorem said, okay, so if the corollary of this theorem is if we can take some distribution function, it is very well imitated discrete distribution at the initial condition, then this ft imitate the n-body distribution always. Is it clear? Because this one is 0, so the distance at time t is always 0. So this is a kind of mathematical justification of Brasov equation.
So you first take the limit n going to infinity, and then the two solutions remain close to one another forever.
Forever.
What is the
Sorry? Sorry?
Lipschitz.
Lipschitz.
It is not Lipschitz.
Lip, so maybe I was wrong. So lip. So this one? Lipschitz, the spelling of Lipschitz. Maybe I was wrong.
No, this is not.
Is it okay?
Why are you writing that? Is there any physical reason to write?
Lipschitz? Why I declared Lipschitz? Because mathematical reason. There's no physical reason. So the goodness of Lipschitz is, for instance, if we consider the equation of dynamical equation, first I introduce something like this. So if this f is Lipschitz, then we have a unique solution, something like that. So mathematically, Lipschitz is a good feature. So this theorem requires the Lipschitz continuity for the gradient, the fourth term.
So what happens in the limit of equality? I mean, in equality you cannot say what your time is. Say that you are putting an upper bound,
Mm-hmm.
but I mean, you still cannot say exact. So, can you say that it will always stay close? I mean, you can put a bound, but it's not very close.
So you mean is it a good boundary or not? Honestly saying, I think this upper bound is the large bound. It's not a precise bound. But anyway, it is enough to consider this kind of justification. So even if this estimation is very large.
Usually the time is a power law. No? The two solutions remain close.
Yeah.
Up to a power time, the divergence is power law, not exponential.
If we consider the Lyapunov exponent, then we have the exponential divergence of the distance. So maybe this one is not so bad.
No, I'm saying that for the HMF model at least, two solutions of the Vlasov equation remain close together at least up to a power law time. No? A time that diverges with power law. No? Into the...
If we consider the order parameter, only order parameter,
order parameter,
then it's okay.
then it's okay.
But now we consider the distribution. So the distance is different, so maybe you can understand. So for instance, m is now the integral of something like this. So this one is okay, but now this theorem says that this part
Much stronger than that.
is stronger than the average one. Okay, and then, I have 3 minutes left. Do you have a question? I can use this one? Okay. Oh, thank you. So, I have announced that I cannot use third blackboard, so I wanted to eliminate the previous description. So everything okay? So now we have a Vlasov equation, and I go to the stationary state of Vlasov equation. So what is the number? So number 4, stationary state. So what is the stationary state, condition to the stationary state? The Vlasov equation is written by using the Poisson bracket. So Poisson bracket is A and B is this. So stationary state, the condition to the stationary state is this part is 0. So F is stationary is defined by this Poisson bracket is 0. And I come back to the derivative notation. Okay, so first I consider so-called homogeneous distribution. So this one is a homogeneous distribution. It means that this distribution does not depend on Q. So especially homogeneous. So this one are the counters of this distribution. So what happens if we consider this spatially homogeneous distribution. Now, F star does not depend on Q, so we can eliminate this part. And next, what is this? So this one does not is not 0. And this part, what happened? So this part is dq and integral of phi q minus q prime and f star p dq dp. Sorry. And what happened? So q prime here, but there is no q prime. So we can modify like this prime and then integral of q prime. And this function phi is a periodic function. So if we integrate over one period, then it becomes constant. Is it clear? So if we integrate a periodic function, then the oscillating part is 0, and 0 Fourier mode remains, but it becomes constant. And then we have derivative. So this part also 0. So it means uniform distribution. So this one is always stationary state. So for any function of p, they're stationary. Yep. State this one.
Yeah, like del F star del Q is 0 because it is homogeneous in Q.
We consider this one.
Yeah.
Yeah.
And then y del H is del Q.
This one.
Yeah.
Okay. So H F star is p square over 2 plus phi q minus q prime f q prime p prime t and dq prime dp prime. So if we perform the q derivative, this part eliminated, and this part is remain, and then so this part is equal to this. And this part does not depend on q prime, so I push out from the integral of q prime. And the remaining part is the periodic function of q. So the remaining part is only 0 Fourier mode of phi, but it's constant. So the constant, derivative of constant is 0. So this is 0. It's clear? So for any homogeneous state is stationary. It is a strong nature of the Brasov equation. And how about in homogeneous state subset this? Can we get a very big family of stationary state or not? The answer is yes. If F star, now it depends on Q also, is described by, this is some function, and I put Hamiltonian. If F star satisfies this, this F star is described by, this F star depend on QP only through the Hamiltonian, so Hamiltonian QP, then this one is stationary state. Why? It's very clear. The condition of stationary state is a Poisson bracket of H and F star. And now F star is a function of F, so H Poisson bracket of H and the function of H is 0. Of course, to get the concrete stationary state, we have to solve this equation. So because F star is here and X star is there, so we have to solve self-constant equation for X star, but it is possible. So if we give some function, then we get stationary state. So for any function f, phi. It's okay?
So if you do not have periodicity, then your homogeneous states are not stationary. I'm not talking about this HMF model.
HMF model?
No,
Okay.
not HMF model.
Not HMF
For
model.
HMF model, I understand the derivation.
Yeah.
If you do not have HMF model, and let's say you add some term by hand,
Yeah.
mean field in nature, but it's not periodic.
So to explain that, I start from HMF, you know. So in the case of HMF, what happened? So this equation is F star equal phi. So now the Hamiltonian is more or less something like this. That's, sorry, potential part is like this. So M vector, so this one is, and this one construct the M vector, and this vector is in this direction, but I moved this order parameter to the 0 because of the symmetry, rotational symmetry of the system. So in that case, just the absolute value here, and I can eliminate the second part. And then so what we don't know is this M. This one is unknown. So we don't need, we need to know this M. So from this, so F star cosine Q integral is M. And then it's and cosine Q. Oh, sorry, dq dp. So we have to solve this equation for one variable M. It's simple. And if we consider the generalized system, then still we have the function. So phi, sorry. So I write the complicated part as a potential. Sorry. And this potential is phi q minus q prime and cosine. Sorry. F q prime p prime t. And this one has this one is a periodic function, so I have the Fourier series expansion. So phi and exponential I n q minus q prime, and f, the same thing. So this part, so this integral, so and exponential I n q prime. So this is more or less the generalized order parameter. So looking this, so this one more or less the same thing. So we have n order parameters. So we have n one unknown order parameter here. So we should construct n equation, simultaneous equation to solve. It's okay? And then we know the subset M1, M2, M3. So we can construct a Hamiltonian. And Once we get Hamiltonian, we get F star.
So the V of it is a function of only Q, no? There is no P. In the single particle Hamiltonian, H of f,
Yeah?
square by 2 plus V of s, which is a function of only Q, no? Or
Which one?
uh,
P?
H of f.
H of F?
So in that, V of s, the term.
A B of F? A B of F?
Function of only Q.
Yeah. So definition is this. So this Q part and the P part is integrated out.
No, you have written T. I'm reading it as T.
Yeah. So remaining variable is Q and T.
Yeah.
So for bad description. So this one is only for Q and P.
Yeah.
What is the conclusion you draw, like choosing that H star?
Hmm?
Choosing that particular H star.
Sorry?
What's the conclusion by choosing that particular H star of H?
So this equation?
Yeah. When you write this V, what is the conclusion?
Conclusion? So it depends on phi. So this phi. So
So you
For-
said something like n order parameters.
So I imagine that if phi is exponential function, so minus beta x or something like that, then this one is a Boltzmann distribution. So I expect m is an equilibrium value. So equilibrium m is the solution of this equation. But it depends on phi. If we change the phi, we have another phi m. So
Can you just explain once what all phi's are allowed? You said Lipschitz bounded. By Lipschitz bounded, the only gradient has to exist, or does it have more properties?
sorry?
For any phi, can we write the Lassov equation?
So which equation? This one?
If you write the Lassov equation,
A Lassov equation?
yeah, in Lassov equation there is a phi, interaction phi. Can we write Lassov equation for any phi?
So phi is the interaction function?
Yeah.
Yeah, so if phi satisfies this condition, then it's okay.
And by this function, it just means the gradient has to exist. The gradient of interaction phi, grad phi,
Yeah?
exists. If it exists, then we can write it.
Yes, so yes. So the condition is just the bounded and the Lipschitz. So if phi satisfies this condition, then we can write down the Lassov equation.
And everything works. I mean, the discussion about stationary states remains unchanged.
Yeah, it's okay for this phi.
Just another question.
Yeah?
Lassov equation is for, I mean, there is DBJK hierarchy,
Yeah.
right? How does I mean, there we cannot close the symbolic distribution. There is a hierarchy.
Yeah?
Here there is no hierarchy.
Yes?
What is the reason for?
Okay, so good question. So we start from Liouville equation. So Liouville equation is plus blah, 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 blah. And then I perform the integration of dq dp2 from dqn dpn. So this is the first performance. And then, so this one is the important part. So Q1, P1, the previous notation is Qn and P1 and Pn equal. If we set this n body distribution like this, so this is just assumption. And then we take some dynamic limit. So after that, we get Brasov. So the answer of your question is the distribution is independent from each other. Okay? So
Is it because it's an all-to-all model?
yes.
Any particle is equivalent to the another particle, and that's why you like this.
So in this system, each particle has the interaction, but the strength of this interaction is 1 over n, very weak in the limit of n to infinity. So this particle accepts the influence from the other particles, but only from mu field, because mu field has the order 1 influence. So it is a reason, I think it is a reason why the Brasov equation corresponds to this independent distribution. It's okay?
You close the first equation by assuming pair factorization and neglecting 2.2 particle correlation.
Yeah. So so we can construct the BBGKY hierarchy, and then final step, at the final step, we forget about the 2-point correlation. Then it is a Brasov equation. Okay. Down, 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 down.
Yeah. So the part where you have written is constant.
That's one. Okay. Further down. So this one?
Yes, yes. I just want to understand correctly whether you can write down Brasov equation for any kind of mean field interaction.
Yes.
But this idea that the X star P in the stationary state works only for the interactions which are periodic in the.
Because see, imagine the Q is not periodic. And is it possible to have a homogeneous, spatially homogeneous distribution?
Yeah.
So it is impossible. Because, for instance, if Q is in R, the homogeneous distribution cannot normalize. So it is impossible. So it is one good comment for the self-gravitating system. Because self-gravitating system is not periodically, spatially periodic. So homogeneous state is not possible. So we have to always consider this spatially non-homogeneous state. So it is a difficult point of self-gravitating system.
If you have a flat potential, then it's possible. No? I mean, a potential that has a flat region. So in that region,
So if we
can be homogeneous.
If we consider the restricted area even in the flat, so for instance 0 to 1 or something like that, then it's okay. So we can consider this kind of homogeneous state. And then in that case, we have to check that homogeneous state is a homogeneous stationary state or not. Now I used strongly the periodicity of this function phi. Okay. Is there a space? And okay, a little bit. And now, almost zero, almost zero space, and almost zero time. So I want to go to the stability. But the stability is a little bit complicated part. So I don't know if I can present all of my statement on stability. Okay. What's the number? Maybe 5? So the basic strategy to analyze the stability is linearization. So we start from the Brasov equation. Now it is Okay. And we consider the stationary state. And we can consider the spatially non-homogeneous stationary state, but it is very difficult. So it's not essentially not difficult, but the computation is very complicated. So for simplicity, I concentrate myself for the spatially homogeneous state. So it means that it is depend on P only. So I expand F around F star plus F. So this F is a perturbation. And linearize the equation around this F star is this. So maybe it's better to minus P Q minus plus F star prime P. So this one is prime. So Q is the previous one, so the potential functional. So this is a linearized equation. And here, so we have in general we have extra term. But again, this one is 0, as we computed previously. So we can neglect this term. And then I write this part as by using the linear operator on the functional space. And what we have to do is to know something eigenvalues of L. Why I do the eigenvalue? Because instead of eigenvalue, in the field of functional analysis, we use the terminology of spectrum. So what is the difference? The definition is more or less same. So the eigenvalues, for instance, we consider eigenvalue of matrix. So it satisfies this. So it means so we have non-zero eigenvector. So it means determinant of this matrix should be 0. So it does say, oh, so this inverse operator of this matrix does not exist. It's the definition of eigenvalue. It's okay? So the same thing for the spectrum. So for the spectrum, if we consider this is a identity operator, and this is my L operator. And if this inverse operator does not exist, then lambda is in spectrum. So this is a definition of spectrum. No difference now? And then we analyze the spectrum of or Brasov operator, so LF. So to analyze this, so I expand this LF into the Fourier series. Oh, sorry. So if we perform the Fourier transform with respect to Q, we get this kind of expression. And what is Ln? Ln acts only on Fn. Fn, what is Fn tilde? So F, I expand Fn, Fq into the Fourier series, and Fn tilde is the Fourier coefficient. So it is the function P. Then the form of Ln, Fn tilde is minus INP Fn tilde plus In F prime extra prime and Fourier component of potential. It depends on Fn tilde. So this is a Fourier component of potential. Is there a definition of the potential function? So no. So we call the Qt. So now I'm considering the static problem of the L operator. So I eliminate T for the moment. And it is definition of it. Small f. So by performing the Fourier transform, also we get 2 pi. So phi n tilde is also the Fourier component of this phi function. And then the P dp. Oh, sorry. So this is a decomposed operator, and so it is clear if one of this operator does not have the inverse operator, then the whole operator L does not have the inverse, because now we have each Fourier mode have the independent equation. So we have to solve for each Fourier mode. So the problem for considering the spectrum, the problem is like this. So we have to consider if this solution, lambda I minus L can be solved or not. So if this solution, equation can be solved, then lambda is not in spectrum. So we consider this equation. So I skipped the detailed computation. The formal solution of this equation is.
If it can be solved, then the inverse exists.
Yes. So if this is solved, then inverse operator of this operator exists. So if we cannot solve this equation, then it says that this inverse operator of this operator does not exist. So lambda is in spectrum. The formal solution is like this. So for each Fourier mode, so where is my Ln? In is the prime divided by lambda plus inp and Vn plus phi n p divided by lambda plus IMP. So this is a formal solution. So how about the spectrum? So if lambda is in pure imaginary axis, then we have a trouble. Why? This part, so 1 over lambda plus INP have a singularity at P equal minus lambda IN. So now lambda is pure imaginary, so this one is real variable. So at this real variable, we have a singularity. So it means we cannot solve because this solution is singular. Oh, it's your time. Sorry?
You can take 5 more minutes.
5 more minutes? Okay, thank you. And then, how about lambda not in IR? In this case, there is no singularity in the formal solution. So it seems good, but it's not true. So we know this function, this scalar value to solve the equation. So what is the value of this one? So we have a definition phi Vn, this one. So to get this Vn tilde, we perform we multiply this formal solution by 2 pi tilde and integrate. So the same thing in the right-hand side, 2 pi phi n tilde and integrate in lambda plus INP. Oh, so maybe it's better. So dp times Vn tilde plus 2 pi phi n, or no space, plus 2 pi phi n, and this function. So now, so this part is Vn tilde. So we have equation for Vn tilde. So we get, so if we introduce lambda function as 1 minus 2 pi phi n and integration of this p, then this equation is written like this. Okay. So what happened? If this function is not 0, then it's okay. We get the value of Vn tilde. But if this function is 0, we have trouble. We cannot solve Vn tilde. So if this function is 0, then lambda is in spectrum. So like this, we can consider the spectrum. And one important comment is now we have lambda in IR is in spectrum, so it means we have continuous also continuous spectrum on the imaginary axis. And then the root of lambda n is a discrete point. And this one, so to describe this figure, I say, so symmetry, so this function has the great symmetry, which is, sorry, what is this? Minus lambda star and minus lambda equal lambda minus n and lambda star and star. So you can check these equalities. So it means if lambda is spectrum, then minus lambda star, minus lambda, and lambda star also. So this is why I put 4 discrete points on the previous picture. So the important point of this analysis is, let's say, like this. So if we have one root of this function, then system should be unstable. So only one possibility to be stable is there is no root of this function. So only continuous if we have only continuous spectrum, then system is stable.
But it is a neutrally stable, right? Because all
Neutrally stable. Because this is a Hamiltonian system, so it's impossible to attract something. So stable state of a Hamiltonian system is always neutrally stable. Okay, so maybe I stop here. So
if there are no further questions, then let us thank the speaker.